Hello, students. Let's start with an exciting question. What happens when you disturb a perfectly balanced system? Just like a seesaw tips when extra weight is added, chemical equilibria too respond dynamically to changes. At equilibrium, the system is balanced, but if concentration, pressure, temperature, or even external conditions change, the balance shifts until a new equilibrium is established. This behavior is beautifully summarized by Le Chatelier's principle, which says when a system at equilibrium experiences a disturbance, it adjusts itself to counteract that change. Today, we'll see how different factors, concentration, pressure, temperature, inert gases, and catalysts affect chemical equilibria and how industries cleverly use these shifts to their advantage.
Imagine we have the reaction hydrogen gas plus iodine gas gives two molecules of hydrogen iodide. Written as H2 gas plus I2 gas forms 2HI gas. If we add extra hydrogen, the system doesn't just sit idle. To restore balance, it consumes some of that hydrogen along with iodine to produce more HI. Similarly, if HI is removed, the system shifts backward, breaking down HI into hydrogen and iodine. This is equilibrium in action, always fighting to undo the imposed change. So, the concentration of added reactants or products is relieved by shifting in the direction that consumes them, while the concentration stress of a removed species is relieved by replenishing it. Now let's make this real with a fascinating color experiment. Consider the equilibrium. Fe3+ ions in solution react with thiocyanate ions to form the deep red complex. The equation is Fe3+ aqueous plus SCN minus aqueous gives FeSCN2 plus aqueous. If you add more thiocyanate, the deep red color intensifies, a clear sign that equilibrium has shifted forward to form more complex. But if oxalic acid is added, which ties up Fe3+ ions, the equilibrium shifts backward and the red color fades. This vivid color change is a classroom demonstration of Le Chatelier's principle. The system resists disturbances by shifting equilibrium accordingly. Next, let's talk about gases. Pressure and volume changes can dramatically alter equilibrium. Consider the reaction. Carbon monoxide plus 3 hydrogen molecules gives methane plus water vapor. CO gas plus 3H2 gas forms CH4 gas plus H2O gas. On the left, we have 4 moles of gas. On the right, only 2. If the container is compressed and volume decreases, the equilibrium shifts toward the side with fewer moles, the forward direction, producing more methane and water. On the other hand, if pressure is reduced, the system shifts backward. So the rule is, higher pressure favors fewer molecules of gas and lower pressure favors more molecules. Temperature plays an even more interesting role because it changes not only the equilibrium position, but also the equilibrium constant itself. Heat can be treated as a reactant in endothermic reactions and as a product in exothermic reactions. Take the Haber process for ammonia. Nitrogen plus 3 hydrogen gives 2 NH3, with DH equal to minus 92.38 kilojoules per mole, meaning it is exothermic. Increasing temperature adds heat, so equilibrium shifts backward, reducing ammonia yield. But lowering temperature favors the forward direction. However, if it gets too cold, the reaction slows down, which is why industrial ammonia synthesis balances temperature and pressure for maximum yield. What about inert gases like argon? If added at constant volume, they don't participate and equilibrium remains unchanged. Only when pressure changes at constant pressure do inert gases have an effect. And catalysts? They're like traffic police, speeding up both forward and backward reactions equally. A catalyst lowers the activation energy, helping equilibrium reach faster, but the equilibrium composition, the actual ratio of products to reactants, stays the same. That's why catalysts are indispensable in industry. They save time and energy, but don't alter the equilibrium constant. So where do we use all this? Everywhere. The Haber process for ammonia, the contact process for sulfuric acid, even removing carbon dioxide in lime production, all rely on Le Chatelier's shifts. In the Haber process, ammonia is continuously removed to keep equilibrium driving forward. In the contact process, temperature and catalysts are carefully balanced for optimum SO3 yield. These principles make large-scale chemical production possible. To summarize, adding or removing reactants and products, changing pressure, altering temperature, or adding inert gases all shift equilibrium in predictable ways. And catalysts? They only help us reach equilibrium faster. That's the power of Le Chatelier's principle, turning abstract balance into practical control for industries worldwide. So to wrap up, equilibrium is never static. It's alive, sensitive, and responsive to change. By applying Le Chatelier's principle, we can predict and control the direction of reactions, from the test tube in your school lab to massive industrial reactors producing fertilizers and fuels. I hope this session helped you see how chemistry is more than equations. It's a living science shaping the materials and processes around us. See you in the next class, where we'll uncover even more fascinating reactions and their real-world connections.